All right, I want to look at an important fact that we're going to need this semester. In particular, we're going to need it for this section. And to show it to you, I need to remind you of the derivative of the dot product of two vector functions. So derivative of r1 dot r2 is r1 prime dot r2 plus r1 dot r2 prime. And keep in mind that the dot product of two vector functions is actually a scalar function, and you see that here. This is a scalar function in t, but still a scalar, not a vector. So here's the claim. So if the length of r of t is always c, if it's always the same length for all t, then the claim is that the derivative r prime is always orthogonal to r. In other words, r prime dot r is 0. And like we just said, that means that they are orthogonal to each other. And now, it's easy to think about this and get a little confused and say, wait. I thought r prime was the tangent vector. How can a tangent vector be orthogonal to the curve? That's not what we're saying, right? So let me show you a picture that might help you. So first off, we need to take a moment and interpret what this really means. The length of r of t is constant. That means that even though you can point any direction you want, any of these r of t's, wherever they go, they're always the same length. You can't have one out there like that. They're always the same length. And so you have some curve, and it's curving through space. That curve actually has to lie on a sphere of radius c. So your curve isn't just wandering through space. Imagine like a ball here. Your curve has to be on the surface of a ball. It can look pretty wild, but it can't just stretch out forever because r of t has to have constant length. Okay, so that's the first picture that I want to show you. The second picture is, let's sort of zoom in on our curve now. We're imagining this curve on the sphere. Here, down here is the origin, and I can go ahead and draw my r of t out, let's say right there. So here's r of t. What we're saying is the vector r of t and the vector r prime of t, which in this case is going to look something like that probably. Here's r prime. Maybe my length isn't right, I don't know. But you can see that the tangent vector, even with my crude drawing where it's a little bit off, the tangent vector can be orthogonal to the position vector r of t. You can be tangent to the curve, but orthogonal to the vector that's putting you on the curve, right? R of t, the tip of that vector puts you on this curve c. So that's what's happening. Now let's go ahead and delete this picture and see if we can see why this is true. So here we go. Let's begin by having a look at r of t dot r of t. This is exactly the length of r of t squared, but we're assuming the length of r of t is constant, and so this is a constant squared. And so now I want us to think about the derivative of r of t dot r of t, and I want to use this fancy formula up here. Let's use that formula. And so since r1 is r2, this is going to be, well, it's going to be r prime dot r plus r dot r prime. And so this is going to be exactly 2 r prime of t dot r of t. You can sort of think of it like that. Okay, that's one perspective. That's cool. The other perspective, though, is that we just showed that r dot r is a constant squared. So this is the same thing as taking the derivative of a constant squared, which hopefully you know by now is 0. And so all of a sudden 0 is this. Well, that means that the inside has to be 0. And so it follows, we can say, let's just say thus, r prime of t dot r of t is 0. 0 scalar, not the 0 vector. So that's how you show that that's true. All right, so how is this useful? Well, let's recall that the unit tangent vector always has length 1. It always has length 1. And so by the result that we just proved, the unit tangent vector t dot t prime is always 0. They're always orthogonal for each other. So the point is, they're always orthogonal to each other. So t prime is always orthogonal to t for all t. That follows as a corollary from what we just showed. So that leads me to define what's called the unit normal vector. And so the unit normal vector for r of t is defined as, we're going to write it as n of t. I'm going to slide this down over here actually so I have more space. N of t is going to be just t prime of t, but I want it to be a unit vector, so I've got to divide by the length of t prime. All right, that's the normal vector. And now when you're thinking about how this looks, I want you to imagine your curve, and I want you to imagine your point. Here's your tangent vector, and so you know that this unit normal vector is made up of t prime divided by its length. So it's orthogonal to this. Here's t. T prime is orthogonal. Which way does it point? Does it point this way or does it point this way? And so the idea is that the normal vector always points into the curve. It's going to lean into the curve. So it's going to point this way. Here's that normal vector n pointing into the curve. And so we can say n points into the curve. Somehow to me I can memorize that. N points into the curve. Okay. And we can also define the binomial vector. We can say, hey, these two guys are orthogonal. Take their cross product and you get another thing that's orthogonal to both of them. And so that leads us to the binomial vector b of t. And b of t is just define the unit tangent vector t cross the unit normal vector n. All right, so I want to begin by finding the unit tangent vector. So this is r prime of t over the length of r prime of t. And this thing is going to be, let's work it out together. So r prime, we can see, is minus the sine of t, cosine of t, and 1. When I want to compute its length, I'm going to divide by the length of this guy. I'm going to get off to the side. Let's do it just kind of in the air here. We're going to get a sine squared t plus cosine squared t plus 1. This is 1, so I'm going to get a root 2. So divide by root 2, and you end up with minus sine of t root 2, cosine of t root 2, and 1 over root 2. So that's the unit tangent vector. For the unit normal vector, I'm going to take t prime of t, big T prime, over the length of big T prime. And so here we go. This is big T, so big T prime is going to be, well, it's going to be minus cosine of t over root 2 minus sine of t over root 2 comma 0, and we're going to divide by the length of this guy. Well, you can see that the length of t prime, the length of this, let's do it to the side here. I'm going to copy this so we can be careful here. I want to take the length of this guy, and so this is 1 over square root times the lengths of the vector minus cosine t minus sine t 0, and this is going to be cosine squared t plus sine squared t, which is just 1. So this part is just 1. So the length of this guy is just, again, 1 over root 2. Let me erase all of my scratch work, but please check with me that you get 1 over root 2. And so the normal vector cleans up as minus cosine t minus sine t comma 0. That's the normal vector. All right, and then finally the binomial vector b of t, I want to take the cross product of this guy. Let's copy this and put it down here, and then this guy. So we'll copy this and put it there. And so we're looking for the unit tangent vector cross the normal vector, and let's see if we can work this out. So we're gonna hide the first column, and we're gonna get minus sine over minus sine t over root 2. And then for the second one, we're gonna hide this one, and we're gonna get let's see, minus and minus makes a plus, but then it's minus again. So we're gonna get minus cosine t over root 2. Hang on, I think this sign was supposed to be positive. Let me check it here. So yeah, 0 minus minus makes a plus, so this should be positive sign. Hopefully you caught that on your own. Minus cosine t, and then we're going to get, let's see, we're going to hide this one, and so we're going to get sine squared over root 2 minus minus plus cosine squared over root 2. Sine squared cosine squared is 1, so I get a 1 over root 2. And you can actually check that the length of b of t will always be 1. And let's just go ahead and say always. Why is that? Well, let me show you quickly. So the length of the binomial vector is the length of t cross n, which is the length of t times the length of n times sine theta, where theta is the angle between them. Well, t is a unit tangent vector, so it has length 1. N is a unit vector, so it has length 1. And they're orthogonal, so sine of the angle between them is sine of pi halves, which is 1. And so you're always going to get 1. So anyway, that's how you do it. And I'll just mention one more thing. When you have a curve like this, you can think of the tangent vector t, the normal vector n pointing in, and then that binomial vector b shooting out. And if you're interested in this and applications of this to physics, actually there's a lot of interesting applications to physics and forces and things like that. You can look at section 10.9 in the book. It's really quite interesting.